And so last week we looked at atoms, atomic structure, and we talked about protons, neutrons, electrons. Today we're going to talk about changes to the atom and what that does. So talk specifically ions and isotopes. So what's an atom made out of? This is a review from last week. Again, red are big keys for this. What I'd recommend is pausing the video and copying it down, then listening to me, because I'm going to talk through it quick, assuming that you've already written it down. So it's made out of protons, which is equal to my atomic number. So for boron, it's 5. Electrons, which is atomic number 5. And neutrons, which is atomic mass rounded. So that would be 11 minus atomic number 5 to give me 6 neutrons in this case for boron. That's an average, which we'll talk about today. So what do you get if you change them? So if I change protons, I get a different element. So hydrogen has 1. Oxygen has 8. Carbon has 6. Nitrogen has 7 protons. And that determines the identity. If you change electrons, so let's look at one atom at a time. So hydrogen here has 1 electron out here. If you took it away, it would have a +1 and no negative ones. It would be a +1 charge. That's an ion. Specifically, when I lose electrons, it's called a cation. Oxygen, if you notice here, is 1, 2, 3, 4, 5, 6 in its outer shell. If it added 2, it would have 10. Then it would have +8, -10 to give me a total of -2 charge, which is a negative charge, and we'll talk about that later. An atom's goal is to get to a full or empty, you can think of, outer shell. So for nitrogen, it has 5 in its outer shell. It wants to add 3 in order to get to 10, just like oxygen. 10 total, including those 2 underneath. If I change neutrons, I get a different mass number. And if it's the same element, like oxygen, if I added a neutron there, its mass would be 17, 8 plus 9. Be still oxygen, but just be a little bit heavier. Okay, that's what an isotope is. It's when I change the mass number, so protons plus neutrons, change the mass number and result in a change of the number of neutrons. Okay, so again, here you got carbon. If you looked at the periodic table, its average mass would be about 12, and that's 6 plus 6. But there's atoms of carbon 13, which has a mass of 13, and 14, which has a mass of 6 plus 8, 14 as well. Call that the nuclear number or the mass number more commonly. So let's look at this. So if we just go to our periodic table and we copy down the average atomic masses, this would get. So bromine, which is number 35, is 79.90. I'm just going to do 2 decimal places. I think that's fine. 79.90. Okay, and pause for a second here and let you find the other two. So go to your Notability app and find your periodic table and find it. Should have figured out those 79.90, 65.39, and lastly 200.59. So when we talk about mass number, if you go back and you look at this slide, it's a whole number. But then you look at the periodic table and you're like, carbon's mass is 12.01. How does it get to be a decimal? Well, you calculate the average atomic mass based on all of these things. That sometimes carbon is carbon 12, sometimes it's 13 and 14. So on average, what is it? Okay, so what we round it to when we round it, so when we're calculating neutrons, I would round this to 80. That's just the most common isotope that you have there. So this would be bromine 80, zinc 65, I'm rounding down in that case, and mercury 201. That's the most common number of neutrons. And the reason why, if I were to subtract, let's say mercury, here's atomic number is 80. It would have 80 protons, right? It would have 80 electrons, but then it would have 120.59 neutrons. 59 for my neutrons. That doesn't make sense, right? So what we do is you round it to the nearest whole, which would be 121 neutrons when I subtract. Okay, so that's why we do that. So again, here when we have helium-5, helium-6, notice the number of neutrons is what's changing, 3, 4, 5, and 6. That's because each isotope is available in different, each isotope is available in different amounts. Okay, so it wouldn't be 25%, 25%, 25%, 25%. It would be like maybe this one's 12.5, that one's 35, that one's 25, and that one's 27.5. Okay, so they're all available in different amounts. That's called its relative abundance. So when you take into consideration the mass, and a relative abundance would be like 0.15 if it was 15%, this one would be 0.25, this one would be like 0.35, and maybe this one is 0.25 as well. When you take into consideration the mass and the relative abundance, you get an average atomic mass. And if you multiplied these and then added them all together, which is the process that they go through, you'd get a decimal number. Let's say for helium, it would then be the average you see in the periodic table, which is 4.005. So clearly my relative abundances aren't accurate. Okay, but that's the idea that you'd go with. So what's the difference between mass number and average atomic mass? Well, mass number is a whole number, right? It's equal to protons plus neutrons. And each isotope has a unique mass number whenever I change the neutrons. But my average atomic mass is the number you find listed on the periodic table, the average of all your isotope, and it's a decimal number. So if I rounded this to the nearest whole, 24, that would be the mass number for magnesium. Or 35, that would be the mass number for chlorine under most situations. And this notation is called isotope notation. We'll look at later. Notice that the top number is the mass number. Bottom number is electrons. So you can get protons, and you don't have to write this down, and electrons here, and then neutrons by subtracting these two numbers. So let's do that really quick. The bottom number is my atomic number, so that's equal to protons, 19, and electrons. Okay. Now the mass number is the top number, so that's 39. And if I subtract mass number, 39, and protons, or atomic number, I get neutrons, which would be 20. Okay. Why don't you try the next three, and then I'll throw them up on screen. Look at these. The bottom number, the atomic number, is equal to protons and electrons. And the mass number minus protons gives me my neutrons. So you'd have to do a simple subtraction problem here for each of these in order to figure out neutrons. Let me know if you have questions on that. So average atomic mass is a weighted average. It's a number, this should probably be in red, that is a decimal. That's an average of all the isotopes. An average of all the isotopes of an element. And we're not going to really go through the process of how to calculate it, but we're going to do it in a lab this week so you can kind of get a sense for that process. It's similar to how I would calculate your grades at the end of the semester. If you have 42.5% from quarter one, 42.5% from quarter two, and 15% from your final, you take that percentage of your grade, 90% times 42.5, and so forth, and add them all together to get your semester grade. So lastly, right here, what I want you to do is go to your periodic table, because we're shifting gears a little bit here, and we're going to talk about valence electrons. These are outermost electrons. Okay. And if you notice, I look at the periodic, these are the blue ones here. We got group number, period number, and then valence electrons right here. So everything in the first column has one valence electron. We'll talk about what those are. Second column is 2. All of these also have 2. So all those in the middle are 2 as well. Until you get to column 13, then you have 3, 4, 5, 6, 7, and 8. The only exception here is that helium has 2. Helium has 2. So add that information to your periodic table, and we'll talk about those here in a second. So pause if you have to go to the next thing. So let's talk about ions. This relates back to valence electrons. So orbitals, these are if we go back to what our atom looks like on a very simple sense, it's the spot where these valence electrons or electrons hang out. Those are orbitals, right? The outermost part of the atom. Valence electrons are the ones that are just in the outermost orbital. So if I look at this one, carbon, which is in column 14, has 4 valence electrons, right? So carbon right here, it's 1, 2, 3, 4 valence electrons. And hydrogen has 1. Okay, so in this case, by sharing, carbon can get to 8, right? 1, 2, 3, 4, 5, 6. By sharing with hydrogen, it gets to 8. And hydrogen, since it's in the first row, gets to 2 by sharing. So the octet rule is, except for hydrogen and helium, all atoms want a full outer shell. Sorry, the exception comes second. So atoms want a full outer shell or orbital valence or valence shell. And the goal is to get to 8, except for hydrogen and helium. They only want how many? First row, they only want 2 valence electrons. Okay? You'll see me use VE as the abbreviation here. It's called the octet rule because we're trying to get to oct or 8. So to get to a full outer level, they either form ions or share electrons. So we already looked at a situation where carbon and hydrogen shared electron. That's called a covalent compound. And other ones form ions. So you see how sodium has one electron in this outer ring. It loses one. So it loses one. And then it exposes this outer ring, which has 2, 4, 6, 8 to it. So that's what we call a cation because it has a positive charge at the end. So ions are formed when atoms fully give away or take electrons. So carbon and hydrogen in this case do not form ions because they're sharing, but sodium does form an ion because it's giving away an electron. And that's what you see. The charge of the ion is what you see in the upper right hand corner as it gives away. So sodium gives away 1 and becomes sodium plus 1. So a cation, these are atoms that lose electrons with a positive charge. These are usually metals on the left side of the staircase. Anions gain electrons, and they have a negative charge. These are usually nonmetals. So notice how fluorine has 7 valence electrons. It wants to add 1. When it does it, creates a -1 charge, but it has a full shell. Sodium has 1 extra on its outermost ring. By giving away, it has 8 in that outer shell for a total charge of +1 though, because it had 11 protons in the middle. So 11 protons plus 10 electrons gives me a +1 charge. Just like here, 9 protons in fluorine, 10 electrons gives me a -1 charge. And those charges become really important when we're talking about forming compounds later. So if you look at the periodic table, for the most part, everything that's first column, they form a +1 charge, if you see that. All these guys here, they form +2. There's kind of a mixed bag here in the middle, and we'll talk about that later in the year. In general, here you'd say that these are +3. Here it's not really anything. Like you see +4 kind of. Here you get -3, but you also have ones that are pluses down here, so that's weird. But in general, we'd say -2, -1, and then 0. Okay, those are the charges that those elements form. So isotope notation tells us the mass number, as we talked about, which is protons plus neutrons, and the atomic number, which is protons and electrons. And then a charge, if there's a charge, it would be right here. This is where the charge would be. And that would tell us if we need to change electrons at all. So let's look at a few examples of that. Make sure you pause and get those notes. So lithium, since it's in the first column, is going to lose 1 electron to form a +1 charge, which is a cation. And barium, which is in the second column, is going to lose 2 electrons, going back to here, barium, to form a +2 charge, which is also a cation. Sulfur, let's go look at it, is right here, is in the 16th column or 6th column. It's going to gain 2 electrons to form a -2 charge. So gain 2 to form a -2 charge, which is called an anion. And I want you to look at the last 3 here and see if you can figure them out. So if you notice the last one, though, is maybe a little confusing. Krypton is a noble gas in the last column, so it doesn't want to gain or lose. It's none of those things. So 0 electrons doesn't form an ion, so it's neutral. But the rest of these, it was gain and gain, 3 and 1 to form -3 and -1, anion and anion. Way to remember these, cation is a T, which is like a positive sign. And then anion has an N in it, like a negative sign. That's a good way to try to remember them. Okay, so now you should go complete the entry 4 homework, which looks like this. You got some of these, and then you got a couple of questions. So let's do one of these together. Let's just pick the iodine one. So this is iodine. Well, hopefully I got enough time. Iodine. And then after the dash comes the mass number from the top. Atomic number is 53. Mass number is the big number, 127. Charge here is a negative sign, that's -1. So protons is equal to atomic number, that's 53. And electrons would be 53, but I have a -1, so I gained 1, so that's 54. Okay. Neutrons are already done. 127 minus 53 gives you 74. Okay, so remember, positive means that you have to change your electrons by losing. Negative means you have to change by gaining. So go ahead and finish the rest of that and this one and submit. and then we will probably go over the answers tomorrow. So if you got questions, that's fine, but just do your best with it today. Okay, bye. Love you.